Our second speaker this morning is Renate Loll from Radboud University Nijmegen. We're very happy to have you here as speaker and looking forward to your talk on nonperturbative quantum gravity from Causal dynamical triangulation.
Very good. So thank you to ABC for having me here as a little bit of an outsider. It'll bring a change of gear. So I'll talk about physics, but of course the physics of quantum gravity and quantum space-time in a non-perturbative regime. So what people call fundamental quantum gravity. So it's to say that, to explain that there's something rather than nothing, but it may look quite different from what you expect, and everyday intuition probably doesn't really reach there. So one of the aims is here to add another data point to your knowledge about. So add a data point to what the string theory is loop quantum gravity and their causal sets, and this is another data point. So that has some specific properties. So I would say this formulation sits a little bit in the sweet spot in the sense that the ingredients are fairly minimalist, so there are no exotic ingredients of any kind, and so one stays close to, in a way, standard geometry as it comes out of GR, and standard quantum theory as in standard quantum field theory, but there's enough ingredients, so it's not so minimalist that you don't get to interesting results. And results is kind of a key notion here, because there are very few results in quantum gravity. So that's maybe a little bit of an exception, but it's of course for you to judge, so I give you some of the evidence. So how is it possible that we can say something new? Because we have computational tools that reach this non-perturbative sector in a way that currently is not done by any other approach in this detail and concreteness. So how is that possible? Well, we're putting the theory on the lattice. Just it took us a little longer than in other theories to learn how to do this properly. And so there's also maybe a new flavor here, namely the role of simulation and computation in understanding the predictions of the theory you're putting ahead. What we just learned from Richard, the string theory, this framework, but we don't really understand what it says in interesting regimes we are interested in. So here we are using another technique to understand what our model actually tells us. Okay, so after this introduction, no, this won't work, but so let me just do this. Oh no, it did work. It did work. Okay, so my perspective. So I reiterate some of the essential points more than once. So there is a functioning theoretical computational framework, and so it's lattice quantum gravity, as I've just mentioned, formulated in terms of this approach, of this tool, causal dynamical triangulations with the handy abbreviation CDT, and it describes four-dimensional quantum gravity as a non-perturbative diffeomorphism invariant quantum field theory of dynamical geometry. So, as I said, no exotic ingredients are here, and there's no proliferation of free parameters, so that's more the minimalist character. We have these numerical experiments that give us a new window we have hitherto not explored of near-Planckian physics, and the often unexpected behavior of the observables that characterize this regime. So it also, en passant, provides a concrete blueprint for what one could mean by emergence of quantum spacetime, and where emergence has a very specific and concrete statistical mechanics meaning from some primordial soup of quantum excitation. So whatever you think of, is there the Planck scale here, so there's a concrete model of what that could be and what kind of results it can lead to. So this gives us, I would claim, a new and very physical, geometrical perspective on quantum gravity. It highlights this non-perturbative character. So here we see also, again, what does it mean going non-perturbative? So you will see what that concretely entails. And there is nevertheless some kind of phenomenology which we hope to relate to real physics, and this will be in a cosmological context. And there has been a lot of progress here. So let's see, with some delay, if I press this button, nothing really happens, but let me press it again. No, I'm going back, okay. I will learn this until the end of the talk. So the next thing is just, I'm highlighting certain things that are important. Many individual words, it's functional, it's computational, as I've already said. It's 4D, it's not a toy model of 2D, which is a big difference, so it's non-perturbative. And its diffeomorphism is a quantum field theory, so it doesn't go beyond quantum field theory. And geometry is dynamical, these numerical experiments, so highlighting various aspects. And to put this in a larger context which I don't have much time or no time to talk about in my talk, like how does it fit with all the other approaches? For instance, there's one of the questions that's addressed in this recent Quantum Gravity in 30 Questions article. So here, again, some key takeaways. So this is an approach where I would claim I can make real progress because there are some new ingredients. So one takes the non-perturbative and also background independent nature seriously, something that nothing much has been said about here in the context of quantum gravity. And so this way of doing lattice quantum gravity is the only way to make sense of the gravitational path integral. So this gravitational path integral is kind of my key tool by which the technical framework, dynamical framework by which I will describe the theory. So of course a very time-honored thing. And you'll also see some formulas coming by, but I won't expose you to many technicalities beyond this. So the crucial thing again here is to go beyond perturbation theory. So how do you do it? And here's a way to do it, by putting the theory on a lattice. So what also turns out to be really essential and was actually at the core of the origin of how we got to this formulation, that it turns out that previous models who were similar but who were in Euclidean space instead of Lorentzian space-time, with similar methodology didn't see anything interesting. So what really was shown by myself and collaborators is if you're putting in information about the presence of causal structure, if you build that into the kind of the microscopic state space of the theory, then you get a totally different theory that is interesting, has an interesting dynamics in 4D, and generates dynamically a four-dimensional space, macroscopic four-dimensional space-time, which is a very non-trivial thing, as I'll go on to explain a little bit later. So the numerical tools are very critical. Without those, we wouldn't know anything about this theory. It would just be formulas on paper whose content we don't understand. Okay, so they reach where other methods, analytical methods, don't. So they're essential, and I think that's a general feature if you want to explore that regime. Now, as a kind of side, what comes with this package is that this regime looks very non-intuitive and looks very unlike, classical GR, and therefore the questions you can meaningfully ask and answer are rather different. And of course it raises the question, so how do you relate it to more classical things? But also what are your expectations of what this theory can do for you? And which of the questions we like of quantum gravity it can actually realistically address. So, and we'll see that requires some adjustment of expectations. Okay? So what it is also, part of the package is, because it's not very classical, it's not perturbative, so G mu nus don't play any role. So what does it mean? Well, you're thrown back onto more general metric structures, and you're forced to express observable properties of quantum space and quantum gravity in terms of these slightly generalized structures, but that is possible. You can nevertheless construct interesting observables that may, in this quantum regime, may behave a priori in an unknown way, which you're finding out through your simulations. And then for some of them, of course, in order to say, well, this theory has something to do with with gravity, right, with GR as we know it, you have to show that at least some of these observables in a suitable limit reproduce things that are familiar from classical theory. So what happens at this scale tends to challenge our classical intuition, and well, that's a feature. And so I would tell you it's a general feature. We just happen to have the tools to make very explicit what it is and what it means. So we are confronted with having to design experiments. So it's very geometrical, it's very physical, and ask the computer certain questions means really formulating an experiment, formulating what an observable is, and you ask a question, and if you're lucky, the computer, in some, of course, with statistical error bars, will be able to give you an answer. But you have to ask clever questions because you have technical limitations, because your computer is not infinite. Yeah. So that's one aspect, and another aspect is something I mentioned already in one of the common sessions yesterday. So there is some actual new mathematics that's associated with going beyond Riemannian, pseudo-Riemannian geometry. Yeah, that comes in here. So, but it's a little bit in the background, but it's part of that. Now I learn. Okay. So what's now the role of the CDT? So I wouldn't say that's an approach to quantum gravity. I would say it's a method. So the approach is just very old-fashioned. It's the superposition principle, the path integral applied to gravity. So there's not much new there. However, to really do that beyond perturbation theory is very challenging, and how to do it. But we solved many technical problems on the way, and I claim now, well, we basically have a very concrete way of doing it, and we are implementing it, and we are running these experiments. And so it has taken us a long time. There are, of course, technical issues involved. But we've arrived now at a point, which I would claim, where now how we treat gravity on the lattice is similar in spirit to how we put QCD and, generally speaking, gauge field theories on the lattice. So the beauty of Wilson's formulation, which I'm quoting here, is the fact that you put it on the lattice, but the essential symmetries, the local gauge symmetries, are maintained exactly. So I would claim CDT does the very same thing with diffeomorphisms. So actually, the methodology is manifestly diffeomorphism invariant, and that's very important in the quantum theory, also at the level of the technical statement, because gauge degrees of freedom, diffeomorphism, freedom, doesn't bother us most of the time, not so much in the classical theory, but it's a huge obstacle in implementing it beyond perturbation theory in the quantum theory. So here is a list of things, that one has to pay attention to, and that explain why it took the community, 20, 25 years to solve all of them, to put gravity on the lattice. So the dynamical nature of space-time, usually you work with rigid lattices, and you just assign, fields to part of your rigid lattice. But the rigid lattice is really, a discretization, if you like, of flat space-time, or after you ubiquitate it, of Euclidean R4. But of course, GR goes further. Geometry is dynamical. So how do you take that into account? The causal nature I have already mentioned. So for technical reasons, many people who put gravity on the lattice did it in Euclidean signature. So there is no causality, there's no notion of time, there are no light cones. And of course, well, it's very questionable that this is the same theory as the true Lorentzian thing. And actually, we were the first to show in the simple toy model that a two-dimensional gravity non-perturbative path integral in Euclidean and Lorentzian signature just gives rise to different results that lie in different universality classes. So what I would also say, what about this, UV completion, what is there? Is this compatible with string theory, with whatever other favorite theories that may say something about not just physics at the Planck scale, but far beyond the Planck scale? Why stop at the Planck scale? Well, as far as we can tell, just from the results we've obtained so far, we're finding that it's a good effective prescription close to the Planck scale. So that's an unusual, thinking of it. So that there is potentially much more beyond the Planck scale, and so but we're going to very high energies. It's because it's kind of an effective theory in the sense of it has certain universal properties, and there might be something beyond there. There may be some implementation of what people call asymptotic safety nearby, something we're trying to ascertain currently, but somewhat independently, we are seeing interesting results that don't just pertain to the classical limit, but to a Planckian or near Planckian regime, and give these unintuitive answers to some of the questions we are asking. Okay, so this has been around for a while, so it's a good data point. We've tested it very thoroughly, including in high dimensions since 2004, so it's a kind of framework that works in a technical sense where, of course, there is in the background there, Monte Carlo simulations and lots of technical questions. How do you do this effectively? Yeah, if you put QCD on the lattice, of course, you have the same type of methodology in the background. So this is very well controlled, and we have experts in our collaboration who are at the top of the game in terms of these technicalities. Okay, so we are not beginners in the tool sense here, and yeah, so we have this unique way now of making quantum gravity into an experimental science. Okay. Now, how does one put quantum gravity correctly on the lattice? So, and what's the underlying logic of how the theory is constructed, this non-perturbative quantum theory. So the lattice, of course, acts as a regulator. So I can write down this path integral, but it doesn't make any sense before I haven't specified all of them. So, think of Q of t, one puts on a lattice, one chooses here such a, let's see, is there the point here? No, yeah, but it's invisible, is it? It's invisible. Yeah, never mind. So this comes from the QCD calculation. So this is a lattice. So and the lattice comes with a UV cutoff, for short distances. So A is just the distance between your lattice vertices, if you like. And this is a discretization and a regularization to make the path integral finite, typically. And then in the end, you want to take A to 0 and understand is there an interesting continuum limit. And that, in order, for things to lose what one calls universality, to lose memory of many of the arbitrary discretization details one puts in, one should do that near a second-order phase transition. So the question is, and the phase transition means the phases refer to where you're sitting in the coupling constant space that is spanned by the bare couplings that sit in the bare action you're putting into the discretized path integral. So this is a typical way of approaching, other quantum field theories on the lattice, but also things like statistical mechanical and dense matter models. Okay. So early work putting things on a four-dimensional lattice really imitated very much QCD. So fixed lattice, and you're just putting typically vierbinds and connections onto that lattice. But this was early to mid-late 80s. They never found anything interesting. They were simulated, etc. So there's a long story about why this is wrong. There's so many sources of why this is not really probably the right thing to do. But you can, against all hope, you just try. Do I see something interesting? One didn't. So the biggest elephant in the room is broken diffeo invariance. There's this lattice, this rigid lattice. So where is diffeomorphism? Where are diffeomorphisms? You don't know where they've gone. You haven't taken care of them. So they're very badly broken. That's something you say. So what does this lattice theory do? And there's also some other issues. When you put things on the lattice, you run Monte Carlo simulations, you need a real framework so that you can talk about probability. So you need Boltzmann weights. So people didn't know how to start from a Lorentzian series, so they put Euclidean gravity on the lattice. So Euclidean gravities, of course, describes four-dimensional curved spaces, not spacetimes. And then also you have an immediate problem, namely that the action, both in Lorentzian and Euclidean signature, is unbounded below. So that's totally different from what happens in gauge field theories. So if you naively just put it on the lattice and you have weights that are e to the minus s, and s is unbounded below, whoops, everything just blows up in your face when you put it on the lattice. Okay? So these are some of the small difficulties in making sense of a lattice gravity theory. So all of these are resolved in this framework, addressed and resolved. Ask me for details about specifics if you're interested. So a key idea that is, how do we get away from rigid lattices, is to make the lattice itself the curved, the stand-in for a curved space-time, which uses an old idea by Regis from the early 1960s, who was interested in describing the dynamics of classical GR, solutions of classical GR, without ever talking about coordinates. So, everyone's dream, get rid of all the gauge degrees of freedom, just formulate everything in terms of pure geometry. And the way to do it is to approximate curved spaces by piecewise flat spaces, where individual building blocks are higher dimensional generalizations of triangles. The triangles, or the simplices, the four simplices in 4 dimensions, they have, by definition, they're flat on the inside, so no interesting structure. So how do you get interesting structure? By gluing them together, pairwise, along, their 3-dimensional faces, and then you pick up kind of where these building blocks meet, you can pick up intrinsic curvature. So that's the beautiful idea. So you can get rid of kind of the smooth structure, the G mu nu. You're getting rid of the coordinates in a way, because all you have to give me in order to, to construct one of these curved spaces is, the building blocks, tell me the edge lengths, and tell me who is next to whom. That's it. So diffeomorphisms don't act anymore on this. So it's kind of pure geometric information. So one of the key things to make things really manifestly diffeomorphic and invariant is just to build your path integral just using these geometric data. Okay. So what form does this take? So here on the right is this kind of the formal expression for the Lorentzian path integral for pure gravity. So I'm not talking about how to couple matter, you can ask me about this. But so this is a very formal thing, so Z is just, just a name for it. Then there is a measure where I'm integrating over all geometries. So geometries are, you can think of them coming from, classical GR as Lorentzian metrics modulo diffeomorphism, so equivalence class under this gauge group. And then, you're supposed to integrate over all of them, and there's e to the is, so you have a big quantum superposition. So this is a statement of intent, but this is totally ill-defined. So you're making sense of this, but this is also, what people call the sum over histories, right? So a history is exactly a space-time geometry, G. Now, what we do, we use the old Regis idea. So we like the edge length and the connectivity that describes these piecewise flat objects. And instead of summing over some ill-defined space of smooth continuum geometries, where we don't really know a priori what to put there, right, for the quantum theory, we just look at it in a regularized way and make a sum over these objects, all objects with certain edge lengths and certain connectivities. So, and what you can also tell, so that would be quantum Regis calculus in a way, but what we're doing is something slightly different. We fix all the edge lengths to same units basically, apart from distinguishing between space and time-like edges. So the edges and the building blocks are kind of all the same, and the sum over geometry is the sum over possible gluings, or in other words, the sum over all possible connectivities. Okay, so you cannot do both. I mean, if you added the edge lengths on top of that, you would be over counting degrees of freedom. So what one does in dynamical triangulation, causal or non-causal, so Euclidean or Lorentzian, is what all goes by the name of random geometry to some extent. Is you have identical building blocks, and your task in the path integral becomes summing over all objects with suitable amplitudes that you can build according to certain gluing rules into piecewise flat approximations of curved spacetimes. So what's important here? So the distinction between, you can do this in a Euclidean way and in a Lorentzian way. So I illustrate this in 2 dimensions. In Euclidean, I mean, you don't care about, there's no time. So you can use equilateral Euclidean triangles and you put them together, okay? And build Euclidean curved objects. So this is a typical member of the ensemble. If you want to go Minkowskian, so that kind of was the added value of CDT, then you choose pieces that are cut out of Minkowski space. So, and it turns out to be convenient to choose them to have time-like edges and space-like edges. And you can already see a flavor. And what you then do in the gluing rules, that's important. Here you can glue anything to anything as long as you adhere to local manifold conditions. Here, you should take care that you don't glue light cones, you know, going this way and gluing that way. So there is a kind of an overall flow of time in the direction, you know, that makes gluing objects glued from this very different from objects glued together from this, generic ones. So, and there's also a nice way of thinking about the Wick rotation, but I don't have time really to go into this. So one important thing, so the elementary building blocks, there are gluing rules. Of course, you start with kind of, you know, with extended objects. So the lengths squared are proportional to the A squared. So that was my UV cutoff. So you try and solve in the path integral by putting these ingredients there, and then you try and see is there anything interesting found when I take A to 0. And that can be done analytically in 2 dimensions for both of those, and the path integrals lead to different results in 2 dimensions. So there was the first evidence that, if you do things in a causal way, maybe it can fix the problems that people found in higher dimensions, trying to generalize the purely Euclidean path integral. And the important thing to realize here, the typical members in the ensemble, you know, of the configuration space of your path integral, they look like this. So that's a stand-in for, you should imagine, so they're very, very non-classical. Think of them as higher dimensional analogs of the Nova differentiable paths that you get in the path integral construction of the path integral for non-relativistic particles, yeah? A la Feynman Higgs. So there's, of course, a mathematical construction which leads to the Wiener measure, where you can show rigorously that, well, the path integral measure is peaked on objects like this. Then you would say, ooh, but these are very, I mean, paths, you know, that are Nova differentiable. How is that compatible, you know, with paths of particles? Well, this is perfectly compatible. These are path integral histories, and physics is in the observable, or the eigenvalues of the observables, and of course they can suitably smeared, suitable choice of observables is perfectly compatible with having the standard classical limit. Okay, yeah, unfortunately, there's a problem here with pictures that are missing, that have gone missing in the process. So yeah, I have to apologize. So there are things that illustrate aspects of this, but which ones are now missing, I'm not so sure. So here are just some details put in. So I gave you the formal path integral before. Here now I'm specifying what action I'm using. So it's standard Einstein-Hilbert action with the curvature term and a cosmological constant term. And in CDT, this becomes now a well-defined object in a regularized sense, where I'm summing over causal triangulations made from 4-dimensional Minkowskian building blocks, which I glue together according to causal gluing rules. And yeah, so I have a simple kind of measure term in there, but otherwise I'm integrating over a straightforward discretization of that action. It's a bare action, you should realize. So it's not a gross bias just to put in the Einstein-Hilbert action, you know, and ignoring higher order curvature terms, because they are generated during renormalization, during taking this A to 0 limit. So this A to 0 limit is very important, because in that limit, interesting things happen. So it's different. So this is not discrete quantum gravity where you pull out of a hat, you know, some, don't ask me, you know, loops or events as your, and your intuition tells you that Spacetime must be made from these things, at a microscopic level. This is, of course, completely arbitrary. So here we're following a different strategy. So we're using certain building blocks that are informed by the degrees of freedom of the classical theory, but then we make sure that we take a non-trivial limit and we are looking for scaling limits exactly near higher order phase transitions where the details drop out. The details, whether that I happen to choose little triangles or not little squares or pentagons, become totally irrelevant in that limit. So that's the charm. Yeah. So if I postulate fundamental discreteness and postulate some Planckian building blocks, that's a typical strategy people choose. Of course, the physics at that scale will be totally related to these choices, and there are just so many different ones. Even if they lead to the same theory, classically, if that could be done, of course they will lead to different Planckian theories. So here is a way to find, if it exists, something like a universal theory that depends on just very few free parameters, namely two that need to be fine-tuned potentially, and find a universal quantum theory that works at the Planck scale, or near the Planck scale. So, and we can put this on the computer, and that's fantastic, right? Because people don't have that.
That's the picture that's kind of missing, right?
Oh yeah, that's the picture that's missing. Yeah, thank you. That's a 4D building block.
Yeah.
Yeah, I don't know. This has happened to me before. That things. But okay, here's a picture that's still there. So what's results? How do we do physics now? As I said, we ask questions. What are questions? Questions are observables. So observables, which are called OG, depending on geometric or metric degrees of freedom. My edge lengths and my connectivity data. That's what they've been translated to. And I insert them into the trace, and I have Wick rotated. Yeah, sorry, yeah. So also an O here is missing there in that line. Observables, oh gosh, yeah, there's a formula missing. So this is tragic. I should have used my computer after all. But so what is standing here is, so this is an observable. I insert it into the trace. This is just a standard way of representing eigenvalues of operators in a path integral approach after I've Wick rotated. So I start Lorentzian, I have a well-defined Wick rotation, and now I'm looking at observable questions I'm asking from this ensemble, if you like. And this is gravity, so it's pure gravity, so there's no reference, well, not even boundaries, because I compactify everything for simplicity. So there's no matter, so there's no way to mark points. And as you know, the point X, is not a physical concept. That's the whole reason why diffeomorphisms are kind of the symmetry or invariance group of this. So certainly an observable that is R of X, R being, let's say, scalar curvature, is not an observable, but, and that's what's written here, the integral over R of X over all of spacetime is an observable. Say, okay, good, but this is a single number. You give me a local quantity like a local curvature, and I have to integrate over all of space, and that's an observable. Yeah, that's the way it is. So that's a feature. Again, it's not a bug, but it's a feature. So it reflects the fact that in this Planckian regime, I would say, or even if, say, we coupled matter to it, this is highly quantum fluctuating and not classical. So even when we put in matter, it's not that they form a nice grid that I could use as coordinates. So yeah, it doesn't really make sense very much, to refer to anything coordinate based. And this now the expectation management part comes in, because many of what people put forward as a question that I would like quantum gravity to answer typically comes from a very classical or semi-classical context. Think I would include singularity resolution even, that says, in certain places stuff happens. Yeah, that's not a very global thing to say. Or things like, resolves the information paradox. Black holes, well, there's already a black hole geometry somewhere in there, and I'm arguing in terms of quantum fields, on that background. There's no background here. This is just highly quantum fluctuating stuff happening near the Planck scale. You can say, okay, right, yeah, so it's just so different from what I understand and know what's the physics of that? Do I even have a grasp of the physics? Yes, you do. And you have to ask the right questions. So what are interesting ways, interesting observables, which I can study in this context? So they have to be, of course, defined operationally in this background field and highly quantum fluctuating setting. And again, I would claim it's not specific, that's a generic feature, it's not specific to this formalism. However, here I have very concrete computational tools, so I can ask these questions and I can address them explicitly and not at some meta level. And that's very educational, okay, to say the least. So, for instance, what happens? What's a Planckian surprise? So, a surprise that so in the sense that people didn't realize for a long time when they were starting to study these in a Euclidean domain. So that's the precursor of this is the kind of Euclidean dynamical triangulation. They were putting together things from four-dimensional building blocks, Euclidean building blocks. You can say, okay, that's maybe not the right thing, but something to start. And then they were looking at what the computer gave them, and they assumed they were looking at a four-dimensional object. But then, kind of doing more numerical experiments, contradictions arose. So, and then they started to ask, okay, maybe this is not a four-dimensional object. Let's measure its Hausdorff dimension. Let's measure its spectral dimension. Spectral dimension is something you determine by a diffusion process in a very general space. So if someone hands you, a very general space with metric properties, so there is some kind of Laplacian operator floating around, you can, a simple question you can ask about, an aspect of the spectrum, and that happens also to be a diffeomorphism in invariant quantities that's well defined in the ensemble, is the spectral dimension. And it basically tells you how fast the random walker, gets after a certain diffusion time away from the origin, and that has a characteristic of the effective dimensionality. So when you did that in this Euclidean game, people realized, oops, this is not a four-dimensional space at all we are looking at. Yeah. So instead, what one found, it's all branch polymer systems that one was studying. Where one thought one was talking about 4D extended geometry, it was just branch polymers. So the CDT part is a way, initially was to say, okay, if you now do things putting in causal structure, may that be a fix for these sicknesses where, so what kind of effect is it? It has nothing to do, it turns out, with that you're putting in the Einstein action as a weight. It has to do with the entropy of states. So you get overwhelmed if you're saying, you have a certain number of building blocks and you must construct all objects you can get, subject to gluing rules from those. Well, in certain parts of phase space, you just get overwhelmed by, say, objects where the building blocks glue together in a way that on a larger scale just looks like a polymer, a giant branch polymer, which has absolutely nothing, whichever way you want to massage it, with four-dimensional extended spacetime. So here you see an effect that you would have never seen or dreamt of just looking at classical and perturbative theory. So this is a feature of the non-perturbative theory, which happens when you allow quantum fluctuations to be large on short scales. And it's what I would call an entropic effect. So it's not it's in the measure, if you like, of the path integral. Here, kind of the entropy part, which competes with energy, which is e to the Euclideanized action. Yeah? So if you're doing classical theory or WKB, then you will only look at kind of the energy part. So where we see interesting physics in this non-perturbative scheme is where kind of there is a balance between what comes from how many states represent a certain weight of the action and the weights themselves. So that's where we see the interesting non-perturbative physics. And CDT now turns out, indeed, to cure the issue that you never saw anything four-dimensional or large scales. So it was shown one can measure, if one does this game in the causal variant with CDT, that putting together four-dimensional building blocks and being in an appropriate part of your phase space, you find actually extended and four-dimensional or large-scale objects. But there is an interesting twist to this. If you look at the spectral dimension, and if you let the random walkers walk for a long time, they effectively see something that's four-dimensional, within measuring accuracy. However, if you just let them probe small regions, kind of Planckian regions, they see an effectively kind of two-dimensional space, again, with statistical error bars. So why is that relevant? Well, here's a predicted quantum signature. Yeah? So here's a dimensionality. You expect it classically to be 4, and that seems to fit in some appropriate large-scale limit with what we're finding. But when you look at small scales, there's a deviation from this classicality, which is a dimension that's not 4, and you could not have dreamt of if you just came from classical or perturbative theory. Okay, so this is part of emergence, but in the true statistical mechanical sense of emergence. So what are other interesting questions I can ask to my dynamically generated, quantum spacetime that sits in the computer? Well, one thing you can ask is how does the volume of the spatial slices, how does it behave, or as a function of time? So you make a snapshot of, you're picking out this one variable. So you're working in a compact situation where you've chosen an a priori topology where your slices are 3 spheres topologically, and you can just monitor what is their volume. And that volume will, of course, quantum fluctuate. And it turns out it does not just quantum fluctuate in a crazy way, but it forms a shape where the time goes to the right, where typically it starts at 0 volume, then the universe becomes extended, and this blob we've measured to be 4-dimensional, and then it goes back to 0. So that's a single snapshot of this single volume variable. So what we then do, we take an expectation value in the ensemble, and then it turns out this has a distinct shape, and the shape is exactly what we call the volume profile of a classical de Sitter cosmological spacetime. So solutions to the Einstein equations with a positive cosmological constant. So here's an example of an observable. Again, we can measure, we extract in this very, very quantum fluctuating regime. So the quantum fluctuations you see here are only those of the 3 volumes. So we've measured them, they're sizable, but they're not huge. So this is not the local geometry. The local geometry still looks like this. And we can match it onto classical expectation, and even more, the fluctuations around those, we can map onto a mini superspace cosmology. So an analytic continuation, and it matches well there. So why is this remarkable? Again, we're starting from first principles. We have these crazily quantum fluctuating objects. We're just asking kind of a simple question: how does the volume behave? And it turns out we can match it onto a classical expectation for sufficiently large extensions. Okay. So is that all we can do? No. In a nutshell, no. We've made progress because a dimensionality, that's nothing much interesting from a geometric classical point of view. The total volume, well, that's interesting from a cosmological point of view, but it doesn't tell you anything about local structure. For a long time, we didn't know really how to characterize local structure very well until we found, motivated by what's been done in pure math, in geometry and metric spaces developments, a notion of quantum Ricci curvature, which it turns out to be a very, very non-trivial thing, because imagine this is nowhere differentiable. If you want to write down Riemann tensor, do you take G mu nu, right? You take 2 derivatives. Well, but if your underlying space is not differentiable, I mean, everything is just, again, blows up in your face, is vastly infinite. So there is a renormalized notion of quantum Ricci curvature. There is a very interesting connection with these mathematical developments. Here I won't explain, but it illustrates the nature of the beast. We're running experiments, we're asking questions, and these are data. Yeah? They're data. Here you see the green. Here is, of course, some error bars. The reds in here are not error bars, so this is the shape of the universe, this is matching to the shape of a Euclidean de Sitter space, and the red thing is the size of the quantum fluctuations. And the reason why the quantum fluctuations are quite large is because the universes, it turns out, we are studying there, are like 20 Planck lengths across. So they're tiny, tiny, tiny. Okay? So that's why these fluctuations are relatively large. So that's some evidence that the universe has some curvature properties in an average sense that match also those of a de Sitter space. So we cannot say that what we are finding there is a de Sitter space because we have only looked at like two variables. We have looked at the dimension, of course, but we have looked at the overall shape, and we are now looking at an average curvature. So that's, of course, by far not enough to say that it is de Sitter space, but it's already pretty non-trivial evidence that it's a good candidate. So where does that take us? In terms of phenomenology, of course, very suggestive of cosmology. Where can we find quantum imprints that may be predicted, I may be able to extract from this framework that I could look for in the CMB today. Okay? So the observables I've talked about until now, well, you could say it's a post-diction. Maybe that the universe is a de Sitter shape, but of course it's a prediction from first principle, which is interesting, but can we say more? What are interesting observables that people in cosmology study? And you will find it's correlation functions. So that's a kind of a magic thing, correlation functions. Of course, if you know, roughly speaking, if you know the correlation functions of the theory, you know the theory in quantum field theory. So we are, of course, applying it to the theory of gravity, but something similar holds. And now that we have a local notion of curvature, what we can do is study curvature correlators. So, yeah, I won't give you a big story about why this is very remarkable, but it comes close to objects one is interested in and works with in early universe cosmology. So the framework is there, QFT on curved space-time. So this is a very different framework, but there is a hope, again, not by comparing formalisms, but comparing the outcomes of certain observables to make predictions. Okay, so this is basically my last slide. Apart from the summary, so again, reiterating some of the points. So key here is I'm using path integral, nothing exotic, but non-perturbative. The causal structure is important, the way I encode curvedness in the lattice is important, and to have a numerical toolbox. There's a change of perspective, so you have to get used to this very non-perturbative world with certain questions that you can formulate, but other questions that, even as a matter of principle, are probably impossible to formulate operationally, but also to answer with the obvious limitations, of course, we have, computationally with the computer. So what's beautiful about it is what I call Einsteinian spirit, because it's metric, it's geometry also slightly generalized. So it's beautiful to be forced also to formulate physics in terms of, really diffio invariant physics. So that's the true physics, the essence of the geometry. So that's very nice. Background and scale have to be generated dynamically, and generic discrete models won't do this, but we have come very far here. So it also throws that's the expectation management thing, but I also would say it throws a new light on what it means to solve quantum gravity and what expectation we can have from a truly fundamental non-perturbative theory. And these may not be the expectations of, as I said, solving the information loss problem or relating to that, but it's really talks about a very different regime, but it doesn't mean that's uninteresting or irrelevant. So what tools do we have, realistically speaking, to describe this regime? I think in terms of analytical methods, they will fall short, apart from maybe formulating effective theories for part of the degrees of freedom there. So I say, again, expectation management. So if you want to become an experimentalist, so here are some ways of doing this. Look at this recent paper on more on CDTs in these reviews, and I have certainly stretched your attention, so thanks for listening to me.
We now have a comment by Nick.
Hit play. Oh, wait 1 minute. do this or? Oh, that can go over here. Great, thank you for this this talk. And I think that this is beautiful, to me, really beautiful work and very interesting. And there are many things that I could ask, but I thought I would. There's sort of two topics I wanted to focus on. Partly to maybe reinforce a couple of things you said. Partly to maybe draw attention to some issues that maybe point to some of the kind of metaphysics-y kind of questions that are here that we could think about, and then partly for things I don't understand. Which one? What are we using to?
Yes, this one, on the side.
On the side you can.
I
think I'll just hit
the
button. So anyway, right. Well, actually, what I was saying that I was supposed to say, I wanted to thank Renate for clarifying the triangulations for us. You've done a very nice kind of job. Obviously, there's a bit more to do because they still have these questions. Okay. So really 2 slides. So first of all, this is sort of more sort of methodological maybe, or sort of thinking about the place of causal dynamical triangulations sort of in different approaches to quantum gravity. So if you're thinking about it, so I think this is the right picture, tell me. So you could sort of think about sort of fundamental or, hoped for UV complete theories of quantum gravity, which sort of exists, don't exist. We've talked about string theory, there's loop quantum gravity, I would say, group field theory, also sort of related in there. So we have that kind of theory. I've left the gap here to put in CDT. Also, kind of quantum gravity is, quantized linear general relativity, sort of background dependent, gravitons living in Minkowski spacetime or de Sitter spacetime, something with suitable sort of symmetries. So that's a sort of a lower energy theory. Has applications, is successful in those applications. Usually those applications have to do with semi-classical gravity. And maybe I should have put semi-classical gravity. Well, no, because I actually want quantum gravity. And I'll also put you can take a limit of that, keeping gravity quantum, I would say. There's sort of debate that takes you into a Newtonian limit. And I'm sort of saying that because, Mike and Nielsen, I wrote a book about how to think about this in these tabletop quantum gravity experiments. And as I understand it, that's where CDT goes, is sort of in that level. Sort of, it's more, it's diffeomorphism invariant, it's background independent, so it's more, gravity-ish than just quantized linear gravity where you have a background, but it's not all the way to sort of UV complete quantum gravity. And so as I understand it, we're supposed to think, one thinks of this as a sort of Wilson renormalizable lattice theory in comparison with QCD on a lattice. And so then, as I understand, that would mean that it is sort of insensitive in the sort of Wilson universality kind of way to what's actually happening in the UV physics. So there'll be a regime in which it applies, and it's explicitly constructed to look at physics that is independent of the sort of details below a certain scale. So I have a question. Or a couple of questions, it's a question sort of related to that. And so it is exactly to get a better understanding of how to understand the relation of CDT to sort of UV complete quantum gravity, about which you're quite sort of scathing, I guess, in some of this. So this is the way I would sort of probe it. So the UV complete quantum gravity, the standard expectation or stated expectation is that different theories of such theories will produce new physics at the Planck scale, Geometric physics won't be sort of applicable at the Planck scale. These theories may disagree at the Planck scale. Given the UV insensitivity of CDT, that seems to say that at the Planck scale, the CDT should be breaking down. It won't be geometric. There are going to be real physical differences that shouldn't be seen in CDT. So I'm kind of interested about the scale at which one goes over from CDT into Planck scale physics. Okay. A sort of second thought is, well, maybe it's before the Planck scale. You know, there's say the string length, or other theories may have other length parameters, and that it might be where you expect to see new physics that isn't picked up by CDT. Okay. Not all the views around here are as beautiful as the others, obviously, but this is the more metaphysical kind of question. So this was about sort of emergence of space-time, and I very much kind of like the way this sort of is how I see it being, introduced in the question of, coming up with sort of observable operators that can be properly operational, understanding it in the framework. And maybe I'll emphasize again in the framework, I mean, you said it several times, but I think I take it really important to realize we're doing a path integral here. We're summing over these diagrams, we're calculating expectation values. Okay, that's what the sort of pictures are, and that's what you need to have in mind. So I think one of the, with all due respect to Kian's talk, right? So one of the aspects of space-time emergence, then let's say focus on dimensionality. That's kind of a nice one that you've talked about here. So Renate mentioned spectral dimensionality. I also recommend the Quantum Gravity in 30 Questions paper, which I'm kind of drawing on here. It really is kind of very nice for understanding, a lot of these issues more. So here's two ways, right? So you can define a spectral distance in terms of the rate at which things disperse. The dimensions are basically the exponents of either time or distance in the case of the Hausdorff dimension, which has to do with how sort of spheres scale as you make them bigger with respect to some distance. So that's what the logarithms are saying there. So we have sort of two intuitive, I take it, sort of operationalized operators for these quantities. They don't have to be four. It's two in the case that you said. They don't even sort of have to agree. So here's a passage, and now you don't have to look at me. Well, I'm here, but this is a passage from the 30 Questions that was sort of addressing this issue. How is it possible that a superposition of spacetimes, each one assembled from four-dimensional simplices, generates a quantum spacetime that's not four-dimensional? One way in which this can happen is that a particular region of phase space, the four simplices preferably arrange themselves into a structure that at the cutoff scale is a four-dimensional manifold by construction, but when viewed from a larger scale, looks like a branched polymer. Okay, so we have this. In this system, then we have a Hausdorff dimension of 2 and a spectral dimension of 4/3. So this is one thing that can happen. I take it in the CDTs that's sort of not going to happen. Reading on the passages there, and I wanted to bring back to this comment from the beginning, which I take it is related to this, and so partly this is a question to give you a bit of opportunity to say a bit more about what's going on here, because I think this is quite nice for the space-time emergence, familiar space-time emergence picture, that the causal structure will sort of stop this from happening. Just to hear a little bit more about that. And it looks like I probably have, that's my question then about how so. Many other things we could talk about, but that's my 5 minutes and probably more. But thanks again for this great talk. This is lovely. Fascinating stuff.
very much for the good questions and the highlights. So I think maybe I can, starting with the previous slide. Will I manage? No.
Yeah, you'll have to go through that again.
Oh, I see. Oh, okay. Oh, when going back, okay. When going back. Oh no. Forward is not the same as backward. Let's see. There's one more line, right? One more bit. Yes. Okay. Okay. So, yeah. So let me clear up. Let me say some general points and maybe clear up some misunderstandings here. So what is special? I mean, if you look at quantum field theories in general, we have 4 fundamental interactions, of which gravity is one. So what distinguishes from a QFT point of view is gravity is that it's not perturbatively renormalizable. So it simply means there is no meaningful way of summing up the perturbation theory. So this, of course, is a fact known since, well, suspected for a long time, but it kind of really shown kind of in the mid-80s, making kind of these two-loop computations. So, and from there also, as is written also up in this 30 question thing, well, then the realization comes, okay, we have to go beyond perturbation theory, but how to do it? There's no one trajectory. And from there, the field of quantum gravity just splits up into, so many different ways of trying to address this and making meaningful of what it means to go non-perturbative. So, but of course, the perturbative non-renormalizability makes it also special when, for instance, you put things on a lattice, because there's a non-commutativity of the limits. So, putting something on the lattice and taking, some naive classical continuum limit just to see that, for instance, that you are properly implementing the action, etc., according to Reggie. That's one thing. But then kind of doing the full sum and then understanding what is the final outcome, which is a kind of the lowest energy state, kind of the vacuum state of the full non-perturbative theory, where not only the weights play a role, but also the entropy, as I tried to sketch. So the theory we get from there is not, that will not reproduce you something that microscopically looks like Minkowski space, or microscopically looks even like de Sitter, constant curvature space, but it will has a very non-trivial, integrate, non-perturbative structure on the shortest scales. So how does then, nevertheless, can classicality emerge? Well, through coarse graining and looking at larger scales. So there's no contradiction in principle. So what is the status with respect? So what happens now at very, very high energies? So of course, so our putting things on the lattice explores a certain range of physical length scales. And we are putting the length scales not in ad hoc, but we are getting to them by looking at certain observables, which have certain semi-classical behavior. This is, in this case, kind of the three volume correlators. And the expected behavior has a certain dependence on Newton's constant. And comparing what we find in the computer with the expected behavior, we find a way of translating lattice units, which are, of course, there are no physical units there, with physical units, which are dimensional, which are lengths. Yeah? And from there comes the statement that we realize, where we are working with very small universes, if you like, or a chunk of space-time, they're up to 20 Planck lengths across, and the resolution we reach is, where we can reliably measure, is in the region maybe of 4 Planck lengths. So we have a window. Okay. So this particular setup is still compatible with 2 types of thinking about what Nick calls the UV completion. So what is UV completion in a way? Well, one way is to say, okay, where are the divergences that we seem to see in the perturbative theory? What happens to them? And is there a way in a regime to come up with finite answers to when we start evaluating observables? And how does the finiteness come about? So one possibility is the existence of UV fixed points of the renormalization group. That means as I crank up the scale, typically this is formulated kind of as a momentum scale, but one can just say if I go to smaller and smaller distances, and if I kind of follow trajectories kind of constant physics in my theory space, I don't get a runaway behavior, for very large momenta, but there is actually, when I follow these trajectories, they end in a fixed point. And this is, of course, the asymptotic safety conjecture that this could be true for gravity. So that is simply a resolution of that issue. And there's, of course, a whole part of the community working with functional renormalization group methods that have established in certain truncations of the full theory the existence of such UV fixed points. So that is very, very non-trivial. So one of the points is in a lattice, one would like, since this always happens in truncation, there are continuum calculations on truncated phase spaces in a sense I cannot go into their truncation. So, and it's difficult to assess the reliability of the truncation within the formalism. That's also a typical situation of physics. With our methodology, we could in principle find independent evidence for the presence of such fixed points. So that is work that is ongoing to compare with the simplest model that comes from the asymptotic safety scenario, where you just again have a truncation with just the Einstein term and a cosmological constant term. And there are some indications that one may be able actually to find, in part of our phase space, the phase space diagram unfortunately also was lost in translation of the CDT model, that one can actually match the thing. So that is one way, which is kind of a clean-cut way to take care without ever going beyond the metric degrees of freedom. You can say, of course, what becomes of those, well, it's just metric, it's G mu doesn't play a role, but still it's those degrees of freedom. So that's one way in which, the whole thing could turn out to confirm this picture. Another, what people often mean by UV completion is, I go to higher and higher energies, and then, whatever, like in certain particle physics examples, new degrees of freedom start popping up. And if I then rewrite, some kind of what the theory is in terms of these new degrees of freedom, I will see that a totally different type of physics takes over. No? And that could be, the physics of some, to say something, some two-dimensional conformal field theory, which you would have never dreamt of just starting from your G mu. So this is also an idea that is very frequently put forward without necessarily filling in what this is. Of course, it could be kind of a string-like thing where then you realize you have to go beyond quantum field theory and to reach all the degrees of freedom. So I would say what we are doing might still be compatible with other stuff that may be happening, beyond the Planck scale at even shorter scales. So here, I don't exactly understand what you mean by Wilson renormalizable. So what's the UV insensitivity? I think there's some misunderstanding here. So what is the idea, for instance, of the what happens in using kind of standard lattice criticality? So let's imagine this this picture of asymptotic safety is true. So what does that mean? Well, we have second order phase transition lines in our phase diagram. So we approach those, and the continuum theory at that very high energy scale is found in the approach to that limit. So it's not at the limiting point. At the limiting point you have conformal, symmetry is realized. So that's not the theory you're looking for, because gravity is not conformally invariant. But you find to lowest order in this lattice space in your EV cutoff, you find that there is your UV theory. Of course, you won't have very explicit analytical control over it, but you can ask your questions through observables. So that's a standard, in a way, we are applying standard logic. And this, in the approach, the theory you get there, in principle, also might depend on other degrees of freedom. It's hard to tell, but what it certainly will have is universal properties. So, but the universal properties do not just pertain to macroscopic properties, maybe that are observables. That was maybe the misunderstanding, but they pertain to things like what is the spectral dimension at the Planck length. So I'm not quite sure what this UV insensitivity, what you had in mind by this, or maybe you can comment on this. You were thinking of just that universality applies to macroscopic observables?
I don't know quite what you mean by macroscope. So,
away
do you
from
mean bigger than the Planck scale?
Anything that's large compared to the Planck scale. So I would. So what this is meant to, achieve is finding universal properties pertaining to physics at the Planck scale. And the limit A, of course, we don't stop with A at the Planck scale, but we take A to 0. You could, So there could be other stuff out there.
Right. So I don't want to take too much time for people, other people's
just
questions.
because it's already a few minutes past them, so maybe that's a good moment to also open.
Well, there's the other slide.
But there's also the other side.
Yeah. Okay. Well, one quick. Okay. Let's talk about scales. Yeah. So I just want to make a drawing. So what's the essence of putting in causality ex Michael? What do I mean by this? I mean that we are arranging let's make this two-dimensional example. Yeah. So my two-dimensional Minkowski building blocks, they had time lag and space like these, and they had a light cone. And I said in passing, you must take care when you start gluing these to not that there's an overall kind of flow of light cones in a time direction. Okay, so the fact in which this is implemented is by saying you have to practically we have a layered structure, all of these CDT histories, where we implement kind of a quantum version, you could say, of a very strict causality relation on the individual path integral histories, which is what's it called? Causality. I mean, the strictest notion of causality, which essentially tells you that your spacetime is topologically the product of a space of fixed topology, spatial topology times a time axis, global hyperbolicity. Okay, so the building blocks have to be arranged such that it's not allowed that the light cones go sideways, if you like. So they have to all go up. And what in particular is this incompatible with? It's incompatible with a space that, as a function of time, splits, into several components. So let's say this is t equal to 0, and then I look at later time steps, and I find there have been branchings, which are where at the next time step, clearly something has happened to the topology of the universe, because here it had one component, and here now it has acquired a second component, it just popped out of nothing. Here it has also another component. So my causal gluing rules, they prevent these histories from contributing in the path integral. I forbid them by hand. You can ask me, what's your rationale? My rationale was, well, this is of course a very strict notion of causality. Let's just see what happens. We don't a priori know, because it's non-perturbative models, what will happen when I make this restriction. But it's a very physically motivated restriction, because these are very acausal and would never be space-times in classical theory because of these causality violating branching points. I mean, to cut a long story short. So what I do is I say, I take the very same path integral, but essentially the only thing I do is I forbid branchings of space-time as a function of time. And of course, if I don't have a notion of time, I can't even do that. So in a Euclidean theory, I can't exclude these things, because there's no way for me to make the argument. So when I do a Euclidean path integral, these things are all there in the sum. And they, in 2D, they give you a beautiful theory, this theory of your gravity. In higher dimensions, they just give you branch polymers and other gibberish. So the thing is, so you, in higher dimensions, you have analogous restrictions on, motivated through causality of the micro, the individual paths into the histories, which themselves are not physical. So this is not a rigorous argument, you say, but you just say, okay, let me do it, and let me see what I find. And I find a totally different continuum theory, which has nice properties where the Euclidean theory just gave, nonsense. So this is the essence, I mean, in a nutshell, the causal structure that I'm putting in, and that seems then compatible with at least some nice, classical limit features of the final quantum theory.
Can I answer to the question very quickly that you asked before? So if I imagine some quantum gravity that's supposed to hold at scale, at scales smaller than the Planck length, whatever that kind of means, it's supposed to be more fundamental. Yet it made a prediction at the Planck scale that disagreed with one of the universal predictions. Then you'd say it was just wrong. Is that right?
Well, it's another theory, but of course no one is even close, I think, to proposing.
Yeah, but then it would just be
but the criterion
with this.
Indeed would be, let's compare observables. Yeah.
Okay. Yeah,
and then you would say, that's right, there is more than just is in my, small parameter space.
Okay.
Thank you very much.
So we've time for just one question, because we have to leave in 5 minutes.
Oops.
So, do you have
That's
a
lunch.
question, Chris? No. So good luck, Nika, to be the one lucky person.
Well, Niels had to stand up for it.
Oh, okay, thank you. Surely a theory can always be UV complete in your second sense, but so let's focus on your first sense, or the fixed point sense.
Yeah.
I'm wondering to what extent does CT require this first sense of UV completion? I mean, so asymptotic safety, you get all these similar results.
Wow.
Yeah,
Some observables can be compared. Yeah.
spectral dimension, for instance, and reduction of that, maybe even the thing about cosmological constant. And I'm just wondering, what happens, so to speak, if the continuum limit does not exist in CDT? I mean, is this an option that, or is it all what's relevant? Is it as if there was this continuum limit, so that you make, so to speak, prior to taking A to 0 some interesting claims anyway. So in some sense you could think of asymptotic safety like as a toy model, so to speak, if you want, but you in your approach don't really require that you even have UV completion as a first step. Is this the right way of thinking of it?
Yeah, but of course, this is based on results we find. So so the asymptotic safety is, let's say, within kind of ideas of conventional QFT, is kind of the distinguished way. Beyond that is of course a bit a question of our imagination of what happens in the UV may be just too limited, and you already see when you get to this non-perturbative regime, well, it's difficult, even what type of language would be suitable. But it might be, as I said, maybe there's hidden some effective theory which, we cannot guess, but we might actually get a hint from, as a matter of principle, if you ask the right question about the right observables. So the only statement here I made is, it seems this is a computational tool, and it gives me in an energy regime or length regime, and at least close to the Planck scale, meaningful results. In the sense, I find this, dimensionality feature. I find, this matching still relatively close to some semi-classical properties. It's not infinite results. So in that sense, effective theory, of course, it's very unusual. Use of the word effective, because usually effective refers to something at much lower energies.
Sure. Yeah.
But here I'm using it in the sense it's an effective theory, and maybe of some even more microscopic stuff that sits out there, and I don't currently know how to reach it computationally because of my limitations.
But first of all, you're indifferent to whether A to 0, so to speak, can be meaningfully taken, right? So it is,
well, what the theory then is in that limit. Yeah. And to what, how it extends, what physical regime that probes. But I would say it's a murky area where it's difficult to, because of our limited, tools or way of thinking about this regime. It may be yet some, totally other idea. People in the past have played around with, the theory becomes maybe topological, the theory becomes fractal, because these are all just words. But other things might happen. If it merges to some kind of fractal regime, then it's kind of interesting. Then it would say, okay, that's what asymptotic safety people have played around with. It's saying, okay, beyond the Planck scale, there's lots of physics there. I can go to smaller and smaller scales, but since everything is, can be mapped onto each other by scale transformation, there's nothing new there. There's stuff there, but it's all fractals, all self-similar. So I would say maybe one could think of it as kind of a third scenario, which is neither one or the other, or maybe compatible with the asymptotic safety thing, because the asymptotic safety thing says, of course, you can go to arbitrarily large k, and just you run into a fixed point. So.
Thank you.
Maybe very briefly, Andy, please.
Yeah. At some point you mentioned that the measure of the path integral can be interpreted as entropy. Can you say what intuition do you have about it?
Yeah, well, this is naturally kind of part of the construction. You see, when I do this non-perturbative path integral, I have a configuration space over which I do the sum, or the integral. So, but I have a sum. But the path integral becomes a discrete sum here. So you have the weights, which are, you recognize it's just e to the, I gravitational action in the Lorentzian. After the recursion, it's e to the minus the action, the Euclideanized action. So, but there, of course, and we have a very simple measure. Roughly speaking, it's a democratic measure where each contributing geometry counts once. Okay? Now, you can, of course, ask, what you should ask is, if I fix now the value of this weight, which knows about the Einstein action, to some value, 58. How many geometries do realize that value? And you see, that gives kind of the entropy effectively that contributes to the measure, because if there's 0 geometries, well, then this behavior will be very suppressed. Because the weights in the path integral, of course, depend on their coupling constant. So this balance between how many states contribute at a given value depends on the choice. This balance depends on the choice of these Baire couplings. And so, but the statement I was then making is in a regime where we see interesting physics, there is a balance. If I would rewrite just the entropy of states as e to the something, that you see it's a kind of competition between these two things in the exponent, and one comes from the entropy, which is kind of really the non-perturbative bit. And if you translate it to continuum language, this would be kind of the measure. Because dg, right, tells you what's the weight of a given g. And here it comes from just counting how many representations are there of a geometry that has a certain weight. So it's quite transparent kind of where this comes from, and that there can be some genuinely new things. So whenever we talk about classical semi-classicality, there is no entropy contribution. We're just looking in the vicinity of a classical solution, and we only look at really what happens with the weights. And then you may, in such an approximation, you may see saddle points, or if you're lucky. If you switch on the full theory, then you will see that, well, this perturbative landscape will get totally washed out, because these entropic effects, what comes from the measure, they give a very strong contribution to what happens, what creates this non-perturbative dynamics that pertains to these very short scales. So this may look very different, and what we're finding is kind of, the mother of all vacuum, which is kind of, the kind of minimum of some effective action. Where the effective action is again effective in the sense of Planckian, Planckian dynamics.
Okay.
Thank you very much.